Hey guys, so today we're going to do rice tables, continuing on with Unit 8 Acquisition 2. So why would we use a rice table? So we would use a rice table if we do not know the equilibrium concentration of all species in the equilibrium mixture. So looking back at the two examples we did yesterday, we were given molar concentrations at equilibrium. For both of these problems, we had molar concentrations at equilibrium. Well, looking at this first problem, we don't have molar concentrations at equilibrium, we have an initial concentration. So that's your key that we need a rice table. If you are given initial concentrations instead of equilibrium concentrations, we need to use a rice table. So rice is just an acronym, so R is for reaction, I is for the initial concentration, C is the change in concentration, and E is going to be the equilibrium concentration. Alright, so let's look at this first example, and we're going to create our rice table. So R is for reaction. I just like to rewrite the reaction so we have it. It helps us keep all of our information organized. Alright, I is for the initial concentration. So I have some initial concentrations that I can plug into my equation. We don't have an initial concentration for our product, but let's think about this. Initially, before the reaction occurs, everything would be a reactant. Before the reactants are allowed to react, we don't have any products. So whenever we are doing a rice table, the initial concentration of your products is always going to be 0. Alright, next, our change in concentration. So we don't know the change in concentration. But what I do know is that as the reaction proceeds, the reactants are going to go down. So I'm always going to put a negative sign or a minus sign for the reactants because their concentration is always going to decrease. And the rate at which it decreases is going to be directly proportional to its stoichiometric coefficient. So I only have 1 mole of hydrogen, so this would be minus 1x. And I'm just going to put x in because I don't know how much it's going to decrease by. Same thing for my other reactant. Reactants are going to get used up, so their concentration is going to decrease. We don't know how much it's going to decrease by, so I'm going to put in x. And my coefficient for iodine, I2, is just 1. Well, the products are going to increase as the reaction proceeds. So we're always going to put a plus sign for our products to show that their concentration is increasing. We are going to put a 2x. Because again, the rate at which it increases is going to be directly proportional to its coefficient from our balanced reaction. Our product is going to form 2 times faster than our reactants get used up. Alright. Lastly, E is the equilibrium concentration. So all that I'm going to do for E is I'm going to take my initial concentration plus my change in concentration, and that will give me my equilibrium concentration. So if I take the initial concentration and subtract the change in concentration, that will tell me my concentration at equilibrium. So all I'm doing for this equilibrium row is I am combining I and C. 0 plus 2x gets me to 2x. Alright, so now my rice table is complete. There's one other piece of information that the problem gives us. We know the concentration of HI at equilibrium. So at equilibrium, the concentration of my product is 1.87 times 10 to the negative third. And that is at equilibrium. Well, I also know that at equilibrium, HI is going to be equal to 2x. So I can set my equilibrium concentration equal to 2x, and now I could solve for x. X is going to be equal to 9.35 times 10 to the negative fourth. Well, once I know x, I could now solve for the equilibrium concentration of both of my reactants. So at equilibrium, the concentration of hydrogen is 1 times 10 to the negative third minus x. And I know that x is equal to 9.35 times 10 to the negative fourth. So that means the molar concentration of hydrogen at equilibrium is 6.50 times 10 to the negative fifth molar. I could do the same thing for iodine. At equilibrium, its concentration is equal to 2 times 10 to the negative third minus x. So its molar concentration would be 1.065 times 10 to the negative third molar. So now I have my equilibrium concentrations. I can finally solve for this problem, which is to solve for Kc. So the first thing we have to do is write our equilibrium expression. So that is going to be equal to products over reactants, each raised to the power equal to their coefficient. So I'm getting this from my balanced reaction. And remember, if we have more than one product or more than one reactant, we multiply them together. Alright, so now all we have to do is plug in our equilibrium concentrations, which are going to be these three values. And I would get 50.5. Alright, pause the video, try the second one on your own. When you're done, unpause and see how you did. Alright, so again, your key that you need to use a rice table is if we are given initial concentrations. Alright, so R is for the reaction. I is for the initial concentration. So initially I have 0.40 molar NO, 0.20 molar O2. And remember, the initial concentration of your products is always going to be 0. Before the reaction occurs, we don't have any products. C in rice is for the change in concentration. Reactants are always going to decrease in concentration, equal to their coefficient from the balanced reaction, and we're always going to plug in x because we don't know how much they are decreasing by. Oxygen has a coefficient of 1, so minus 1x. And my product has a coefficient of 2, so plus 2x. For our equilibrium rho, we're just going to take the initial concentration and the change in concentration and combine those together. Alright, looking at our problem, I have an equilibrium concentration of my product. So I know at equilibrium, the concentration of nitrogen dioxide is 0.12 molar. Sorry guys. Alright. I know at equilibrium, my molar concentration of nitrogen dioxide is 0.12 molar. And I also know that at equilibrium, it's going to be equal to 2x. So I can solve for x, divide both sides by 2, and x is going to be equal to 0.06. So now that I know the change in concentration, I can now solve for the molar concentration of each reactant at equilibrium. So 0.40 minus 2x gives me 0.28 molar. And I can do the same thing for oxygen. At equilibrium, its concentration would be equal to 0.20 minus x. X is 0.06. So my molar concentration would be 0.14 molar. Alright, so we need to solve for Kc. So first step is to write our equilibrium expression. Concentration of products over reactants, each raised to the power equal to their coefficient. And then last step is to plug in our molar concentrations at equilibrium that we just solved for. And rounding to two significant figures, we should get 1.3. Alright, last one. This problem is going to be a little bit different. We're still going to use a Rice table because I notice it gives me initial concentrations. But the difference for this one is it tells me what Kc is going to be equal to. Alright, so let's go through, fill out our Rice table, figure out what we know. Alright, so my reaction vessel initially contains 2.0 molar iodine, 2.0 molar bromine, and I know that the initial concentration of my product is always going to be 0. Alright, we can figure out the change in concentration from my balanced reaction. So reactants are always going to decrease. Products are always going to increase, and we're going to bring down those coefficients from the balanced reaction. All right. So now, this is normally where we would solve for x, but I don't have the equilibrium concentration of any of the species in my reaction, so I can't solve for x. But what I can do is write my equilibrium expression based on my balanced reaction. So products over reactants, each raised to the power equal to its coefficient. And what I can do is plug in what I know at equilibrium. So that is going to give me 2x squared all over iodine times bromine. So what the problem did tell me is that my equilibrium expression for concentration is going to be equal to 100. So I can plug in 100 for Kc. So 100 is going to be equal to 2x squared. And then I'm going to combine my denominator. So 2.0 minus x times 2.0 minus x is 2.0 minus x squared. So how we can solve for this is by taking the square root of both sides. So that's now going to give me 10 is equal to 2x over 2 minus x. And now we can solve for x. So x is equal to 1.67. So lastly, let's go back to the question. We want to calculate the equilibrium concentration for each species. So let's start with iodine. At equilibrium, its concentration is going to be equal to 2.0 minus x. So its molar concentration is 0.33 molar. We could do the same thing for bromine. Again, its molar concentration at equilibrium is equal to 2 minus x. And again, x is 1.67. And then lastly, for my product, my molar concentration at equilibrium would be 2x. So these three would be my answers. These are my molar concentration of each species at equilibrium.